angle subtended theorem. The angle subtended theorem states that the angle subtended by an arc at the center of a circle is double the size of the angle subtended by the same arc at the circle. What this theorem is trying to tell us is that if this angle is x, then this angle is 2x. Now let's see some examples. In this diagram, we can see that the red arc at the bottom subtends two angles, the blue one at the center and the red one at the circumference. We can see, as per the theorem, the angle at the center is always double the angle at the circumference. Now, let me change the angle at the center. You can see the angle at the circumference also changes, and it will be half the angle at the center. Another example, this time the angle at the center is 124.6 and the angle at the circumference is 62.3, which is exactly half of the angle at the center. Now, let's look at the proof to this theorem. In order to prove this theorem, I will connect C and O and extend it a little bit to point M. Now looking closer, we see that OA, OB and OC are all radii of the circle. Because of this, triangle ACO and COB are isosceles. Now let angle ACO be x. Because it's isosceles, angle CAO will also be x. Now let's name this y and this will also be y. Because angle AOM is the exterior angle of the triangle ACO, angle AOM has to be equal to angle ACO plus angle CAO. Because ACO and CAO are both equal to x, we can substitute in this equation to get AOM as 2x. Similarly, BOM is an exterior angle to triangle COB. So, angle BOM equal to angle BCO plus angle CBO. Because both these angles are equal to y, we substitute, leaving us with angle BOM equal to 2y. The angle at the circumference is ACB, which is equal to x plus y. And the angle at the center is angle AOB, which is equal to 2x plus 2y. Factoring 2, we get AOB is equal to 2 into x plus y. Because x plus y is equal to angle ACB, we can rewrite this as angle AOB equal to 2 into angle ACB, which is the proof of this theorem. An extension of this theorem is an angle subtended by the diameter or semicircle on any point of a circle is 90 degrees. In this diagram, we have to prove that angle ACB equal to 90 degrees. We know that AOB is a diameter and that it's a straight line. So angle AOB has to be 180 degrees. Because the angle subtended at the center is twice the angle subtended at the arc, and angle AOB is the angle subtended at the center, ACB has to be 90 degrees. This theorem says that the angles in the same segment of a circle are equal. Let's try to understand this theorem before we try to prove it. In this diagram, you can see that there is an red arc and it subtends two angles at the circumference, both of which are equal according to the theorem. Now, if I shorten or lengthen the arc, you can see that the two angles are always equal. Let's prove this. In this diagram, we see that the arc BD subtends two angles, angle C and angle E. We need to prove that angle BCD is equal to angle BED. In order to prove this, let's connect AB and AD. Now, arc BD subtends angle BAD at the center and angle BCD at the circumference. Because of the previous theorem, that is, the angle at the center is twice the angle at the circumference. If angle BCD is x, then angle BAD has to be 2x. As we can see, angle BED is also an angle at the circumference for the arc BD. Because of the previous theorem, it has to be half the amount of angle BAD and half of 2x is x. So angle BED is equal to x. Now, because angle BCD and angle BED are both equal to x, they must be equal. And that's the proof. Tangent theorem. The tangent theorem states that if two tangents are drawn from the same point outside the circle, then they are equal in length. In this case, that means CE equal to CB. Before we dive into the proof, let's look at some more examples of this theorem. In this diagram, we have a circle with two tangents which originate from an exterior point. As you can see, the tangents' length are both 6. Now, if I move this around a little bit, you can see that the two lengths of the tangents are always equal. Let's do the proof for this theorem. We need to prove that side CE equal to CB. In order to do this, let's connect the center of the circle A to points E, B and C. We know that any line from the center of the circle connecting to a tangent always intersects at 90 degrees. So, triangle CEA and ABC have to be right angle triangles. Because AE and AB are radii of the circle, they have to be equal. And AC is a common side. So, triangles AEC and ABC are congruent to each other by RHS. That means that CE has to equal CB.